Well, good morning, folks. So my name is Andy Shamaji. I'm a research scientist here. And I'm going to be giving a little talk about a little introduction to programming, a little introduction to sort of more of a computational way of thinking about things. I'm going to be, and if you guys want me to change this, I'm happy to do so. But basically how I'm going to be setting up the screen here is I'm going to have the PowerPoint in one window, and I'm going to switch back and forth to our Python interpreter quite a bit. So I'm going to basically try and arrange them on the screen, and I'll do the best I can to try and arrange them so that everything shows up at once. But it's, I think because a lot of what I'm going to be doing is going to be fairly interactive, it's a good way to have both the slides and the actual stuff that I'm doing showing up at the same time. Okay.
Are there notes to this, or is this being recorded? It looks like it's being go back.
Yes, this is being recorded. Okay, now, I have a lot of slides here. This is actually more about 8 or 9 hours worth of material here. So as soon as we're done here, I am going to post all the slides online on the web page, where you can download them and look at them as a reference and so forth. Okay. So if you guys want to do so, and believe there are some people also joining us online. So we have the actual Zoom link where this is actually being recorded and streamed live on the internet, and we're all going to be famous YouTube stars. Okay. So I'm going to go over a number of different topics here, but probably the big idea of why, you're probably asking why I'm here to learn computational biology. Why do I have to learn all this computer programming stuff? Well, basically the reason why is because that's when we look around us in the actual physical world around us, we see that the world itself is made up of many, many different objects. And the key idea there is when you're looking at different objects, whether those be atoms or individual agents in some sort of a petri dish, or planets or stars, the main idea is that all of them occur at the same time. Every single entity in the universe moves forward in time all at the same time. So there's a key concept there of everything occurs in nature simultaneously. We have what's called simultaneity there. When we currently how modern computers are, computers don't really do concurrent execution super well. And certainly when we write down a program or when we write down a description of it, we have to use a sequential description of things. So we have to specify things to computer as a sequence of operations that occur one after the other. Now, that's a key difference in how we think about things, is when we think about things in nature, we think about objects and we think about how they're interconnected with each other. And when we conceptualize building a model, we think of building these connections between things rather than actually writing down computer code. Now, we're not there yet. I'm actually working on a number of different I'm actually working on an approach that does let you do literally exactly that, of let you think in terms of objects and then connect them with relationships without having to do programming. That probably won't be ready for general use for about maybe 3 or 4 months or so. We'll have a demo version. If you stay tuned to the Computational website, that's actually a package that I'm integrating in, but I'm not going to cover that right now. So basically, what we have right now is we need to think about things in terms of sequential stream of instructions where we don't have better abstractions. the first thing we're going to do is we are going to install a Python development environment. And this is the same development environment that we are going to use when we write chemical network models that we will attach to cells. So this is actually a package called Tellurium. So if you guys want to go to tellurium.analogmachine.org, we can grab a download link to it. Then you want to click on the install link, which is sort of at the top towards the middle. And then it should scroll the page down to where it should look something like this. You'll have these three options: an IDE front end based on Spider, a notebook front end, and a Python pip package. So are you guys here yet? Or you know what, if you guys have another Python environment that you are actually using, you can use that one also. I'm not going to be doing anything fancy. I'm just going to be running some basic commands and running some basic files. So if you already use something like PyCharm or some other environment that you're happy with, that's perfectly fine. So when you click on the front end based on Spider, you might have to scroll down a bit, and then there's another link where we want to go to the Python 3.6 I wish we had an actual direct link, but we don't. They sort of changed the website around a bit. Okay. So do you guys see the Python 3.6? Okay. So on Windows, that one will download a executable installer that should be about 500 meg or so. We can go ahead and just run that exe, and that will install the whole package. It's actually nice because it installs Python, it installs the IDE, it installs libroadrunner, which is the package that we're going to use to do subcellular models. That will probably take about a minute, couple minutes to install, and we'll just go ahead and let that go. The only thing we need is just a plain basic Python interpreter window where you can just run some commands. That's all we need right now. Okay. Okay. So we'll do a bit of an overview right now. So can you guys see this? Let me try and make the font bigger on this. We'll do a quick overview. I mean, if you're using Spider/Tellurium, it should look something like this, where in the bottom corner, we'll actually have a window where we can enter commands. So we can do, I'll do a really, really quick one. We'll do print hello. And I will explain what this command does here shortly, but basically the idea is in this lower left corner, that's where we enter our actual statements that we want to evaluate, and then we see the result right there. This window here, this is where you can actually have a full script where you can write this one, and you'll be able to actually run this one. This has some pre-built code in here. We can just highlight it all and delete that. And then we can just write a statement here like this: print quotes, and run this guy. Okay, so let me explain to you what exactly happened here. Okay. So this little pane window here, this is where we see your actual statements that we evaluate, and we type those statements here. And you can interactively edit commands, interactively edit statements, and it's really convenient for doing little interactive use. This window here, however, this is where you actually have an actual file that you can actually edit. You can actually write lines in here just like you would any normal text editor like Word or whatever. And this one actually gets saved, and you can actually run this one. They both have their advantages. So if we're just interactively experimenting with stuff, we have a variable and we want to play around with it, we want to look at stuff. Interactively writing commands here lets you play around with it, and it gives you more of an interactive exploratory feel. If you have more of an idea of what you want to do, and basically rule of thumb is if anything you want to run is 1 or 2 statements long, this one's more convenient. If I give you an exercise and that'll end up being about 3-4 lines or so longer, then this one will probably be more convenient. And it's really just whichever one you're more comfortable with. It really makes no difference. But anyway, in either case, the result gets displayed right here. So why don't I have all of you guys just do this? In this window here, just type print, open parens, quotes, hello, quotes, close parens, and we'll run that statement. And hopefully that should just print hello here. And then we'll do the same thing in the file one, where you guys can actually type that statement here in the file, and then press the little arrow running button, the little green running button there. And what that one does is that actually reads that file and executes all the statements in that file. Sort of make sense? Okay, great. Oops. So what did we just do there? So we wrote some little funny looking words in a computer screen, and we got some output. Well, what we did was we actually invoked a built-in function, and we gave it some arguments. And I will go into more detail about what that is here. But basically, when we explain things to a machine in such a way that a machine can understand it, we need to think in terms of defining variables and storing data in there and operating on them. Okay? So, okay. So where can things go wrong? So the easiest errors to catch are what are called syntactic errors. So programming languages, just like human languages, have certain rules where if in English, a sentence should have a subject, a verb, and an object, and some proper punctuation. Statements in a computer language are pretty similar, except they have much more rigorous rules than an English sentence would. So when we make an error, say we misspell something, say we use the wrong operators, say we use the wrong punctuation or whatnot, those are really easy errors to catch, easy errors to catch, and that will result in a syntactic error where right away you'll see, hey, you made a mistake, and you'll catch it. Then the more subtle ones are what are called semantic errors. So these are where the program is actually technically valid, but it does the wrong thing. So it runs, but it gives you the wrong result. And tracking these kinds of errors down will certainly require a little bit more experience and a little bit more patience of looking into what exactly went wrong. Okay. So when we actually write these sort of programs, we are going to be basically dealing with effectively three different concepts. So the first one is programs manipulate objects. So an object is actually a thing that we instantiate. So we'll write funny little statements where we'll do x equals 10, y equals 23, whatnot. So we'll do funny little statements like that. And what we're actually doing there is we're actually creating objects, we're actually creating things. Each one of those things that we create, it has a very special property called a type. So what a type of an object is, it defines what kind of object it is. So the type of things. The type of this thing, it's a microphone. The type of this thing, it's a podium. Everything that we create, every object that we create will be an instance of a type. So if you look around you, we have many, many different cups on tables around us. Each one of those cups is an object, and that is an instance of the type cup. Okay. Now what programs do is they manipulate those actual instances. And we manipulate those instances via what are called functions. And functions are little blocks of code that are predefined where you give them objects and they can perform some calculation on them and usually generate some new objects that are returned to you. And I know this sounds very abstract, but it's going to be clear here in a few minutes. Okay. So we're going to work with our most basic kinds of objects now, and these are what are called scalar objects. So these are individual atomic things that only have only a single element of one. Okay. So the basic ones we have built in we have integers. So integers are basically the set of counting numbers. So these are whole numbers, and they can go from about negative 16 some odd million or so to plus 60 million or so. Actually, technically, they go beyond there, but anyway, so they're actually integer numbers. And then we also have a concept of floating point numbers, and these are, as you might guess, these have a decimal point in there. These are where we represent, these are approximations to actual fractional numbers.
Is there a double in a single float, or is it all double precision?
Yes, and usually when we type like 3.7, that usually creates a 32-bit floating point number. But it has some smarts in there where they get extended to double as needed.
Okay, so don't worry about
we're not going to worry about numerical precision.
or memory.
Yeah, we're not going to worry about memory usage or any low-level details for now. We have the Boolean type, which allows us to represent a true and a false. The none type, you'll probably encounter this quite frequently. For those of you with other languages, this may be a fairly new concept, but an object can be an instance of none, and that's where it's basically a placeholder. It's a symbol. We've defined X, but it's none. It doesn't refer to anything, but its type is actually none, if that makes sense. It's basically the empty set. Okay. And then we can use the built-in function called type to check out what kind of object we have. So we can do this like so, and you'll watch what I'm doing here. So we'll do x equals 1, I equals 23.5, j equals true, s equals, S equals hello. Okay, let's ask a question. What type is my X? So we can do type X. Hey, that's an integer. Type, that's a float. String, okay. So that's how we can figure out what I'll actually use the word kind and type interchangeably. Now we can also ask other questions about our objects. We can ask questions of what exact properties do they have. So we can take a directory, dir, S, okay. So what did this give us here? So I called the built-in dir function. Actually, I'll do dir. Okay. So I called the built-in dir function on my object called X, and they gave us this big list of all these funny little functions, okay? And I'll go over these things at the end of the course, but these are actually built-in functions that are attached to that object that you can call. So yeah, so basically the two big things you might find useful is calling the type function to figure out what kind it is, and calling dir to figure out what is available that you can do with it. We can convert objects of one kind to another. We can't, when we try and convert things, this won't always work, but it will work a lot of the times, okay? So let's convert 3 to a float. Okay, so we have float. We give it the name of the type that we want, 3. Okay, and that converted my integer to a float. We can do int, we can do int. Okay, so I gave a floating point number there, and I converted that to an integer. And when we do that, well, when we convert a float to an integer, it does a chop. It chops all the digits off. What about a string? Can we convert a string to a number? Stir is the name of the string type. Well, that's already a string. That works fine. But what if I want to convert that to an integer or a float? Float so that converted my string to an actual floating point type. What if I give it garbage? How about not? Okay. So if we look at the string, not a number, well, that's obviously cannot be converted to a string directly because it doesn't mean a string. So what happened here is this raise an error. And at the end of, in a couple hours, I'll actually show you how to deal with these sort of issues of how to actually handle errors. But this is what happens when you try and perform an operation that doesn't make sense. Okay. So I need to try and speed things up. Okay. So we already went over printing to the console. We use the built-in print function. Okay. So expressions. Expressions is probably the most common thing we'll do. And it has a pretty simple, we already went over one basic operation. We already went over one basic expression, and that was the assignment expression. So let's do a little bit of analysis of what we actually did there. So what happens when I do x equals, what happens here? We have an expression. That expression has three things in it. It has the name of the variable, it has the equal sign, and it has some other value. That expression, the equal sign there basically says, take whatever is on the left side and make the right side reference that one. So that's called an assignment expression. And we can do many, many different kinds of combinations of this. We can add things, we can subtract them, do the product, division, remainder. The double star is exponentiation. Okay. And I'm going to make all of these available online, so I am going to go pretty fast here. So, okay. There are simple operator precedence rules. So when I type something like, let's do this, 1, what am I going to get here? 1 plus 1 times 5. Am I going to get 10 or am I going to get 6? Why? Multiplication has a higher precedence than addition, yeah. So you can look these up. Do not write code like this. Do not take advantage of operator precedence because it can be confusing and ambiguous. And that is an extremely easy place to make mistakes. I recommend doing this. It does not change the result, but what you've done here by adding parentheses around it is you've made what you're writing more clear. You've made it less ambiguous. Well, actually, you made it immediately obvious to another person reading this what exactly was your intent. Okay. Okay, we can do comparison operators. So all these should be fairly self-explanatory. We can check if things are greater, less than. Double equal tests for equality. Bang equal tests for not equality. We have the standard logic operators, so not, and or. Here we actually have to spell out the actual logic operators. Okay, so I'm not going to do that. So binding. So I can bind symbol names to values. So I can bind pi to 3.14. Okay. Okay. I can rebind names. So certain languages do not let you reassign values, reassign names after you've used them, but here we can reuse the name as many times as we like. Okay. So open. Okay, so we've covered the basic built-in atomic or scalar types. So now we're going to start looking at sequence types. So sequence types are exactly as they sound, where they are actually an ordered sequence of simpler types. So the most common ones, the most common sequence types we'll use strings. A string is the simplest sequence type. A string is nothing more than an ordered set of characters. We'll use lists a lot. Lists are an ordered sequence of objects. You will use tuples from time to time. And okay, so we have a number of different operations we can use on strings. We can concatenate strings, so forth. So we can do A equals some stuff, A plus more stuff. Okay, what happened here? Okay. So we'll notice that many of the built-in operators, not only do they work on primitive objects, but they also work on complex things like composite objects, sequence types, various other things. The meaning of the operator is usually only obvious when we're dealing with simple types. So when I do something like 1 plus 1, that is obvious that we're adding two numbers. When you do some list plus some list, what that ends up doing is actually creating another list that's actually the two of them blatted together. Many other types do have operators that act on them, but you will have to look up what exactly that means when you add them. So such as when we look at the matrix type, would the plus operator, if I add two matrices together, would you expect them to actually create a matrix that are the rows concatenated or the columns concatenated? Or would they do a scalar add on them? Well, for those sort of things, more complex types, I recommend you looking up the documentation on that type of what exactly the operator does. Okay. Oh no, where'd my PowerPoint go? Okay. Okay. We can call the built-in len function to return the length of a list. So we can do len of stuff. Okay. Indexing. Python is a zero-based indexing language. Those of you coming from MATLAB or Fortran, those are one-based indexing. Virtually every other language out there is zero-based indexing. It's just the way it is. I'm not going to, the language designers they had different ideas of what makes the most sense. The Python designers they thought that zero-based indexing makes the most sense, and that's just the way it is. So we can do A equals 1, 2, 3. Okay, so A square bracket 0. If I give it a 0 in a square bracket, that gives me the first element out of that. So A2 would give me the last one. What if I do A index 3? What do you think will happen? Let's find out. Ah, we got an out of range. Yeah. What about this? A -1. What do you think the -1 value is? Yeah, we wrap around to the beginning. Yeah, so we can do a negative indexing, which are going in reverse order. Okay, so we can do A -2, A -3. So we can access elements both starting at the beginning and going forward, or starting at the back and going backwards. Okay. So if you prefer one-based indexing like Fortran, you can always just add a negative in there. Really confuse people. Okay. Okay. You will likely use slicing quite a bit. Slicing, it's a really powerful concept where you use the syntax of square bracket, start, colon, stop, and an optional step. And what slicing does is that creates another list that is a slice or a chunk of that. So let's take a look at, actually, you don't want to have it on the slide here. Okay. So what I can do, I can make a string or any list of stuff, honestly. I'll like this A, B, C, D, E, F, G, H. I take a slice of this from 3 to 6. Okay. What this slice does is it starts at the 3 position, which is D, and then it goes up to the 6 position. So it grabs that little sub-range. If I do the optional step in there, that goes from start, stop, and it skips every other one. I can do this funny little thing where I can have 2 colons in there. What that means is when I don't give it any number arguments, it grabs me everything in there. So effectively, I've made a copy of that list. Okay, and I will go over, there's actually a subtle difference between making a copy of something and creating a variable name and having it refer to it. And you know what? I'll actually go ahead and do that right now. I have some slides later on, but I think this is a good time to introduce the concept of aliasing versus directly referring to things. I have A equals 1, 2, 3. That's my string, okay? Now, you know what? I'm actually going to go talk about lists first because strings are a certain kind of special thing, okay? So strings are immutable. So this means once I've created a string, I cannot change any elements in there. You're not allowed to actually modify strings after you've created them. Okay. You will be using print a lot. Okay. So print is a built-in function where you give print a set of arguments, And all those arguments will then be written out to your console. So you can print X, you can give a bunch of strings in there, strings, numbers, whatnot, and the type of argument that you give to string, it doesn't really matter because print is pretty smart in that it figures out the type of the object you're giving it, and it uses the appropriate behavior to format that so it's written out onto the console nicely. So if you ever use something like C or whatnot, you have to do all of the funny little operators in there and printfs and so forth. But this one takes care of all that for you. You might use input some. Input is a way of receiving input from the console. What input does is when you issue, when you call the input function, that effectively pauses execution of your program up until the user enters something, okay? So I'm going to give a little example here. And let's see if this will work right. So if I just run this with the run, it just runs, it prints out hello. Okay. But I can do input wait for some stuff. Okay, so why didn't my hello print? Anybody? Because we're waiting there at that input line to finish. We're waiting for me to go there and press enter, and then it continues execution. Okay. So you're saying, well, that's not terribly useful. Well, actually, yeah, it is, because we can do in, or I'll just do X equals input. Okay, print hello entered, comma, X. Okay, so we're going to wait for some input there. I'm going to type 6. And that input read whatever the user wrote there and stored that in this new variable here called X. And then I use that value in print. So I print out something and I comma and I give it X. So I just simply echo back what the user wrote. Okay. So we talked about strings. Strings are the most basic kind of sequence type we have. Then we also have tuples. Tuples are an immutable sequence. So we create tuples with the parenthesis function. I mean, with the parenthesis operators. Okay. So we can create an empty tuple, just empty tuple there. We can do t equals open parens and some sequence of stuff that we want to stick together. Tuples are useful when you want to create basically an object that is a set of things that are ordered together in an ordered sequence. And the big difference between tuples and lists that I'll get to is tuples are immutable. Once you create a tuple, you cannot change values that are in there. And you say, why would I possibly want to do that? Well, tuples have much lower overhead than lists. And tuples are the only way that I can, in many cases, they're a very convenient way for returning multiple values from functions. Okay, we can do things like this with tuples. So I can do A comma B comma C equals okay. So I did A, B. Tuples let me do multiple assignments like that in a single statement. So it's a convenient way for doing these sort of assignments. Swap is probably an extremely good example of why tuples are useful. If we have, say, two variables and we want to swap what they refer to, so basically what we want to do is we want to do X and store Y in that, and then Y store X in that. What happens if I try and do this? Well, I've taken the value of Y and I stored it in X. But the original value that X had is now gone. I've overwritten it, it's just gone. So when I try and do Y equals X, it's just gonna get that back. So normally when I do swap, I need a temporary variable to make a temporary copy of my original one. I take my original one, stick it in my new one, take the other new one, and I stick my temp in it. That should be fairly obvious. But with tuples, I can do this really convenient thing of doing xy equals yx. Just swap them right there. So basically, it effectively creates a temporary tuple or a transient intermediate tuple that exists only whilst that expression is evaluating. And once that expression evaluates, the actual tuple that was used there goes away, and you're just left with those variables that are swapped. Okay. Lists are probably one of the most commonly used things that you will use. Okay. We create lists using the, we both create and access lists using the square brackets. So we can make an empty list with just an empty square bracket. Lists are heterogeneous. So we can have a list, and we commonly do, that has numbers, characters, more numbers, lists, tuples, all sorts of other stuff. We can store any kind of object we want in a list. We can grab the length of the list by calling the built-in len function. We can access elements using the square bracket indexing. We can grab an element and do stuff with it. Okay, we'll grab a last element. Okay. And you can actually do negative indexing, which I talked about earlier. You probably won't be using it much, but it's just there, just to know about. We can change elements in a list. Yeah. Yes, yes. In fact, the square bracket operators, those are an operator, and they work on tuples, they work on lists, and many other kinds of objects also support the square bracket indexing. I'm not going to go over into the more advanced kinds of objects, but basically in Python you have effectively three sets of operators. You have the squiggle bracket operators, and those are what we use to create sets and dictionaries that I will cover here in probably about a half hour or so. We have the square bracket, and square brackets are when we do anything, any sort of sequence types. So square brackets are how we both create and access lists. And then we have the parens, and those are used to create tuples, and they are used to indicate operator precedence, and they are used when we define functions and classes. So effectively four sets of four syntax classes of operators. We have the parenthesis, we have quotation marks for dealing with strings, parenthesis for dealing with function calls and tuples, square brackets for creating and accessing lists, and curly braces for creating dictionaries. And then we have the colon, and the colon is used for ranges of things. Quotes are used for strings, yeah. It does not, that does not generate a list, but what that does is it defines a slice. So I cannot use the colon outside of a list indexing operation. If I wanted to create a list, I use range, yeah. So if I want to create, I would use, so if I do 1:5, that's an illegal operation that won't actually do anything. But if I want to do range, that gives me an actual list. Why did that not work? They changed it a bit. Previous versions of Python, range actually returned a true actual list. In newer versions, they subtly changed it where range is actually a first-class range object rather than actually generating a list. And they do that for basically reasons of efficiency. Because if range actually generates a list, well, that's going to allocate some memory, it's going to do a bunch of stuff, and it's going to be pretty inefficient. But normally, I mean, 99.999% of the time, you will use range. You will use it for iterating over a sequence of numbers. So it's wasteful to actually create a list and do all that stuff. So they change it so it's actually a first-class object. Yes. Remember, because we're using zero-based indexing. Yeah. So we started 1, and we're going to generate, and that's going to be our stopping one. Yeah. Or we can do steps and so forth. If you want to do range on floats, I'm going to cover NumPy in a little bit, but unlike MATLAB, Python does not have intrinsic support for floating point operations like MATLAB does. But all of that functionality is there if we include the NumPy or NumPy package. So I'm going to skip ahead a little bit, but in Python, everything is arranged into packages. So I can do import NumPy as n, okay? So that imported a package, and I named it n. So now all these, so that's going to have a set of functions in there that we can actually call and do useful things with. So NumPy has the arrange built-in function, and I'll show you these. So I do n.arrange 0, 3. Okay. So that actually created an array starting at 0 with 3 elements. 5. Okay. Ah, that didn't work. Okay. So we can start. So we can start at 2 and go up to 3. So we gave it the start and we gave it the stop. Okay. In MATLAB, I believe it's start and however many elements, right? Or is MATLAB start and stop also? I don't remember. Yeah, in MATLAB, yeah. Oh, yeah, for start and stop. Oh, okay, as opposed to number of elements. Oh, okay, so A range is the same as MATLAB's colon. Okay. Or we can do start, stop, comma, 0.1, and step sizes. Okay. So the couple subtle differences is range will give you back basically a range, but it only operates on integers, whereas a range operates on floating point numbers. Okay. So lists are mutable, and it's pretty easy. So I do A equals 1, comma 2, oops. That was a syntactic error. Okay. So we have A. A is a list that has 1, 2, potato, 4, and 5. Okay. So now I can actually overwrite elements out of this. So I can do A1 equals some other value. Okay. So I can actually write values into there. Pretty straightforward. Okay. So we have the append. So if we want to add elements to the end of a list, the array, okay, so I'm introducing a new concept now. So we've used built-in functions where we call a function and we pass stuff to it. Many data types also have functions that are attached to that object. And normally we refer to functions that are attached to objects as methods. There really is no hard, fast rule of when something is a freestanding function or when something is a function attached to an object. So, little subtle difference in syntax is if we do len a, I call the len function, I pass it a, and it gives me back 5. But I can do a dot, and in Spider, when I do tab, that gives me a drop-down list of all of the methods that are attached to that object. So we can various other ones. So let's just do append since that's what I talked about. A dot append, and then new stuff. Okay. Usually when you call a method that's attached to an object, that will often modify that object. When you pass objects to functions, those functions generally won't modify that object itself. Okay, so we can delete elements out of here. Delete A2. Okay, so what did I do here? I deleted the item, add the second, or actually the third item there becomes 0. So I can do del, and that removes an item from a list. And that's unfortunately a command that you do. So you'll encounter certain things that are functions. You will encounter certain things that are methods on object, and you will encounter certain things that are standalone commands like this. And that's just something you'll sort of have to do a little bit of reading of which one's which. So I'm just giving you a heads up that there are different packages written by different people somehow have different approaches to doing things. Okay. So we can remove items. We can concatenate lists together with a plus. Okay. So if we want to make a new list, we can do, so this is A. So A plus 3. I cannot add a list and a number. But I now have a new list that consists of my old list and another list that were concatenated together. Okay. And my original list is unchanged. But if I actually wanted to append that number to my list, I have a number of different ways of doing that. I could either do A equals A plus 3 like so. So I've created a new list and I've reassigned my name to it. Okay. I can delete the last element, A. I remove that item. Or I could do A dot append. Okay. So you see how I did the same thing using 2 different approaches? Okay, that makes sense? Okay, great. All right. So we, okay. So if we want to remove items from a list, we can either use del or we can use remove. Okay. So if we look at how to remove things, so what do you suppose will happen if I do A dot remove? What will happen here? Any guesses? Let's take a look. A dot remove 5. remove actually removes the object from the list that is that object. So I can do a dot remove a. Okay. What if I do a dot remove give me a value error? That is not in my list, so I can't remove it. Okay? So, to remove stuff from a list, if we know the exact position where we want to remove it at, we use del. If we, let's just say we know the thing that we're actually removing, but we have no idea where in the list it is, it will remove that thing. So what if I do this? A equals 1. There's A. When I do a remove, it removes the first instance of that thing that it finds and then just says, hey, that's good enough, I'm done. Okay. That's just the way it is. Okay. Okay. So that allows you to actually remove elements. Okay. We can split strings into lists. You probably won't be using this too much. Okay. You can sort lists. I doubt you'll be sorting lists much. You can sort them in place. You can reverse them in place. Okay. So this aliases, these are a subtle little thing that we need to worry about. Okay. So let me go over what aliases are. So we have my list A, B equals A. So now I have two symbols that actually refer to the same object in memory.